Hello, I am the founder of Advanced Materials Applications, and I am the CASIS-sponsored principal investigator for the project that I'm calling Gumsticks in Space. So there is a significant need for terrestrial computing power in space. Currently, space-qualified computers are about 2 to 3 generations or more behind current terrestrial processing technologies. They tend to be very expensive, and they're much larger in size, weight, and power consumption than terrestrial computers. A good example is shown up here. The Proton 200K is sold by Microsemi, and it's about 10 by 16 centimeters. It uses about 5 watts of power. This is a DSP board, and it costs about $120,000. This is a space-qualified computer. The Gumsticks here is a system on a chip. It has DSP, it has graphics processor capability, and it has, of course, the general CPU, in addition to a lot of other functionalities. These are significantly smaller. It's a gumstick size. So it's about 6 by 2 centimeters. Each unit costs about $100 to $200, and it consumes less than 1 watt of power. So you can already see there's a significant value to go from the traditional computer to more of a terrestrial computer. There's actually a significant need, as I mentioned, for more computationally capable computers in space, because there's a growing need for signal processing and analysis, data capture, and sensing and detection for current and future missions. So I've already mentioned some of the benefits of Gumsticks for application to space. So they're very small and lightweight, and low power consumption, and fairly inexpensive. In addition, they use the current generation OMAP processors with ARM Cortex-A8 architecture. They've been currently used in supercomputers, robotics, and unmanned air vehicles, so they're very much out in industry currently. In addition, they're being studied by Honeywell for use in a space-based dependable multiprocessor. And this picture in the upper right shows actually the DM prototype that they're going to fly into space at some point, and that contains 8 Gumsticks. So this study is significant because it is the first of its kind to be published. So there's not been any ground-based radiation studies that have been published. There hasn't been any space-based studies. So we will be doing this within the next year. So our experiment is going to be flying on the International Space Station, and this is kind of a blow-up of the external module. This will be the first experiment to fly on the external module of the nanoracks. This will be in space for about 6 months. So the key questions we want to answer is, how does the low Earth orbit space environment affect these terrestrial-based processors? So in low Earth orbit, there are heavy ions and there are protons that actually can cause a range of different single event effects. And this can actually lead to failure. So we need to understand, given the environment in space, how can we protect these Gumsticks and make these things reliable to work up there? We also want to know, what is the net operation time for each of these modules we're going to test? And finally, we would like to know if the module performance is affected by feature size. So there tends to be a trend that the smaller the feature size, the more single event effects can occur, and this can lead to less operation time. So we're going to be testing a 45 nanometer feature size model and a 65 nanometer feature size model, so we'll see if there's some sort of dependence there. So in our experiment, we're going to test 4 different models: the sandstorm, the earth, the water, the fire. And we're going to be looking at a range of different features and how they function. That would be the general purpose processor, CPU, the RAM, the flash, the graphics processor, Wi-Fi, and Bluetooth. So each of these gun sticks are going to be connected to a radiation-hard watchdog circuit, and this circuit will serve two purposes. It'll protect the gun sticks from catastrophic damage, and it'll also record significant events, which will include high current latch-up or single event functional interrupts. And for those of you not familiar with radiation effects in electronics, high current latch-up is when there's a radiation event that actually causes a short in a MOSFET, which is the foundation of all this processor technology. And this can lead to a current draw within the circuit and can actually lead to catastrophic failure. So we're going to be watching for current rise, and we're going to stop it before it causes failure. And then we're also going to be looking for single event upsets and low current, what we call SEFIs, single event functional interrupts. And those are caused, basically radiation comes in and can flip a bit. And if it flips a bit in an operating part of the chip, then it actually can cause it to stop responding. So the watchdog's going to be looking for periodic heartbeat. If it doesn't see it, then it's going to cycle the power to the gun stick and restore function. And the cool thing is we can downlink the data in semi-real time from the watchdog, from the ISS back to Earth, so we can actually see what's going on during that 6-month exposure. So the timeline for our experiment, the program was initiated last month through CASIS, and from July to December we'll be testing at Crocker Nuclear Laboratories. They have a proton cyclotron there. So we'll be testing the gun sticks and the gun sticks with the watchdog to make sure they're worthy to go into space. We'll be delivering this to NanoRacks about January timeframe next year. And then we'll be launched into space about mid-next year, and it should also arrive soon after that to the International Space Station. So the net exposure is about 6 months. It will be, as I mentioned, it's on the external rack of the ISS. We will have a protective cover on it, so it won't be exposed directly to atomic oxygen and other corrosive gaseous species. So NanoRacks will help kind of make that payload space-worthy for us. And then it'll be returned, and we'll report on the post-flight analysis when it returns in 2015. Thank you.